Okay, so we're going to get into a proof of the insolubility of the quintic and higher now. Um, this is a little bit more technical than what we've been doing, so you shouldn't expect me to ask you serious questions like this on an exam, but nevertheless, it's important to see. So we did a review of the symmetric and alternating groups in class. Let me just remind you, Sn is a set of all permutations of the set 1 to n. So for example, S1 is just trivial. S2 is the identity and the element that swaps 1 and 2. S3 is the identity, the element that swaps 1 and 2, the element that swaps 1 and 3, the element that swaps 2 and 3, the element that cycles through 1, 2, and 3 in that order, and the element that cycles 1, 3, and 2 in that order, and so on. In general, we saw in class the order of Sn is n factorial. Okay? And the symmetric groups are very important. And so that's Sn. We also have the alternating group, which consists of all even permutations. So we saw a couple of ways of representing this in class. The standard way is, for example, if you have a cycle, I'm just going to say like I, J, K, L, you can write that as, let's see, I don't remember if this is the right order. I think this is the right order. You can write it as a product of transpositions like that. So this is I goes to J, good, both sides sends I to J. Where does the right-hand side send J? Well, J is going to go to I, and the next guy sends I to K, and this one will leave K alone. So this will send J to K. Similarly, this guy fixes K, this one sends K to I, this one sends I to L, so it sends K to L, and then lastly, this fixes L, this fixes L, this sends L to I. So they're the same thing on both sides. And in general, you can do this. If you have some I1, IL, you can rewrite that as I1, IL, I1, iota 1, iota L minus 1, iota 1, iota L minus 2, and so on. Okay. And so any cycle you can write as a product of transpositions, and a permutation is even if it can be written as an even number of transpositions. And again, you've all seen this before, but just a quick reminder, transpositions. An even number of transpositions. Now, said slightly differently, another way of viewing this is what an even permutation is we saw that elements, well, permutations can really be thought of as permutation matrices. And as permutation matrices, this can be an n by n matrix. You can look at its determinant. And a permutation is even if the determinant of the corresponding permutation matrix is 1. And we saw that in class, so I'm not going to rehash it. The determinant is sometimes also called the sign homomorphism, but it's a very concrete linear algebra construction. And so AN is a set of all even permutations. Well, A1, there's only the trivial guy. A2, we don't get anything because the only element of S2 that's not the identity is 1, 2. That's an odd number of transpositions. A3 is going to be the identity 1, 2, 3, which we can think of as 1, 3, 1, 2. It's an even number of transpositions, and 1, 3, 2. A4 is the identity. We get the various 3 cycles and their inverses. 1, 2, 3, 1, 2, 4. What else? 2, 3, 4. And we get the ones that are not 3 cycles, that are disjoint transpositions multiplied together. Okay, so just a quick review of the symmetric and alternating groups.